In this lecture, I'm going to walk you through chapter 17, which introduces mixture models, finite mixture models. So this is a very useful modeling tool for situations where you have possibly more than one underlying distribution generating the data, but the proportion in which these two distributions are involved in producing the data is a parameter that needs to be estimated. So, um, so this is chapter 17 in the textbook. So be sure to read that eventually. But basically, we are interested in um, modeling a situation like this. So here, so let's look at this equation here. So what we have is we are observing some dependent variable, for example, reaction time or response time or something. And what's happening is that this response time is either coming from a distribution of probability from a likelihood, let's say call it P1 with some parameters theta 1, or it's coming from um, another likelihood function with parameters theta 2, right? So these two distributions are in a kind of mixture, and what you're observing is perhaps a log normally distributed type of shape, but you don't know where the data are coming from for every data point. One data point might be coming from this distribution, another one from this distribution. And so the way one typically writes this is that there is an indicator variable, call it Zn or Zn, n is the nth data point, that's coming from a Bernoulli with some probability value. So with some probability we are getting data from this distribution. With some probability we are getting data from this other distribution. And so this indicator variable, so if it's a Bernoulli, you'll get a 1 or 0. That tells you, this indicator variable tells you whether we're getting data from here or from here. So if z in the nth trial, if z is 1, happens to be 1, then we're getting data from this distribution. If z in the nth trial happens to be 0, then we're getting data from this distribution. This is a very useful way to summarize a finite mixture model. Of course, you can have more than two distributions, but in this chapter we only talk about this case because it gets harder and harder to model the data if you have more than two distributions, I mean in the face of sparse data, which is usually our situation. So, um, so this is a very useful way to summarize the finite mixture process because it makes it easy to generate simulated data, right? So we'll just take a look at that in a moment. So, so what we are going to have to estimate is this theta probability, and of course these vectors of thetas, right? So these are all the parameters in the model that we have to figure out, get posteriors on. Now, one problem in Stan is that one issue with Stan is because it uses Hamiltonian Monte Carlo, it cannot deal with discrete parameters. So these are discrete parameters, and for that reason, um, what we're going to have to do is we're going to marginalize out these discrete. These are also can be seen as parameters, right? Because if it's a 1 or a 0 in each trial. So we're going to marginalize this out, as I will just show you, in order to use Stan. But I mean, there you can easily find code in JAGs in particular or WinBugs where they illustrate PyMC3 also and Turing, where they illustrate how you can uh, get posteriors on discrete parameters. So in these programming languages, you can model the discrete parameters directly, and maybe I'll I'll show you an example piece of code from JAX, because in the old days before Stan came along, I used to use JAX for modeling mixture processes. So there I was directly modeling the um, discrete parameter. So I should have some code somewhere. So I'll take a look and show it in class. So in any case, what we're going to do is we are going to marginalize out the discrete parameter. And so this is an alternative way to write the mixture process. So theta is the probability of getting data from this distribution, and 1 minus theta is the probability of getting data from this distribution. So what we have is a weighted sum, weighted by the probabilities that produces the observed data given the theta parameters, which is, these all these parameters taken together. Okay, so so that's the other way to talk about this mixture process. Okay, and that's how we will operate actually. So the example data set that we're going to work with is um, some data that involves a fast guess model. So so the data looks like this, though the design of the experiment is like this. It's called the global motion detection task. And so what happens is that the participant might see something like this on the screen. So there are some dots, and the dots are moving. Um, Most of the dots are moving in a random direction, and there is one dot that is moving in a particular direction. It's not moving randomly, right? So you can imagine some Brownian motion where things are moving all in all kinds of directions. So there, you see that they're all moving in all kinds of directions. But these black dots, of course, they're not marked in the experiment as such, but some dots are moving in only one direction. So your the subject's task is to uh, to figure out what the overall direction of movement is of the dots that are moving in a particular direction. Okay, so right or left and so on, right? And then you can make this task more difficult by having many dots that are moving in one particular direction, or very few dots that are moving in another direction. So it becomes harder to tell what the direction of movement is if you make the task harder by reducing the number of dots, right? So this would be easy because you'd be seeing everything moving in one direction. This would be harder, right? So this is the data. This is what the data will look like, and the theoretical assumption for the generative process that is assumed for this kind of task is, so this is called the fast guess model, and this assumes that uh, this is a choice task. So you have to decide which way the dots that are moving systematically, which direction they're moving in. So it's governed by two different cognitive processes. So one process is a guessing mode where you have no idea, right? And you just say, oh, right or left, right? And another is the task engaged mode where you are focusing on the task and you are able to identify the direction. Of course, you might still identify it incorrectly, but you're at least involved and mentally engaged here. So what can happen is that a participant, if you have multiple trials, a participant might not always be task engaged. In some trials they start to get exhausted, might back off to a guessing mode. And then overall they might be task engaged because participants generally try to do their best. When they do an experiment, but there are mental timeouts, and so you lose focus and you don't know what's you don't engage with the task, and so you guess. So these are two possible situations that you might be in as a participant. So we want to model this, right? So of course uh, it could be that the amount of engagement that you're involved in, how much engagement you have, is a function of the task difficulty, right? But for simplicity, right now we're going to ignore the possibility that the accuracy of the choice is affected by the difficulty of the task. Okay, so um, but later on there'll be an exercise on this that we can look at. So the data set looks like this. Okay, so this is Allman's fast guess model. So the data look like this. We'll load the data set from the bcoxi package as usual. And so here we have the subject IDs. We have the task difficulty, easy or hard. And then another thing that they do in the experiment is that they give instructions to the participant to either um, go as fast as they can, or to be as accurate as they can. So they are modulating the subject's behavior. This is called a speed accuracy trade-off, right? So if you focus on speed, you will make more mistakes. If you focus on accuracy, you will take longer to make the decision, right? So we have reaction time, and then of course we have accuracy, because that will be affected by what the emphasis is, whether we are emphasizing speed or accuracy. Okay. So that's the setup. Now, of course, theoretically, you might think that, oh, there will be a bimodal distribution, right? When we plot the data. But what we see is this kind of log normally distributed, data. So there's no way to know like whether this is a mixture or not. You can't always see a mixture. Sometimes you can see a mixture process, right? If they're very different distributions, then you'll see two bumps like a bimodal distribution. But if the means are very close to each other, then you will see what looks like a unimodal distribution, but underlyingly there could be two uh, distributions that are producing the data, but they're not visible. So our job through the stand model is to reveal those two underlying distributions and the proportions in which data are coming from each distribution. Okay, so that's the goal here. So it's non-trivial, right? So if you look at the data itself, what you'll see is this. So what you're looking at here on the y-axis is the response time, and the upper rows are the easy tasks and the lower rows are the hard tasks. And within the easy tasks, either you have an accuracy focus for the participant, or you have a speed focus for the participant. And similarly, in the hard task, you might ask the participant to focus on accuracy or ask them to focus on speed. So one thing to notice is that and on the x-axis you have the accuracy. This is inaccurate, this is accurate. So what you'll notice is that when the response is inaccurate, generally speaking, right? Let's just look at this plot here, right here. Easy cases and accuracy. This is 0, this is 1. Inaccurate, accurate. What you see is that the inaccurate responses tend to be somewhat faster. The accurate responses have a slightly higher mean, right? You can see this bigger spread going up to 3000 milliseconds, and these are crushed towards, the 1000 range here with a few extreme values here, okay? And you'll see that pattern everywhere. Here also you see this. Here also you see this, because this dense part is much more compressed in the incorrect responses. Here it's not so clear actually. Okay, so so the way we will set this up is that we're going to assume that when the participant is engaged, we're going to assume that the participant is going to be affected by the difficulty, which is x sub n here, right? That's the easy, hard, levels of the factor difficulty. And so the response time or the reaction time is going to come from a log normal with some grand mean and some sum coded, difficulty level plus minus 0.5, and the slope will tell us what the effect of difficulty is on the reaction time. So standard, type of model that we've seen before. And of course, you can add hierarchical structure here, but we are ignoring that right now. Okay. So, and then the other distribution where you're doing fast guessing is also coming from a log normal, but this time the fast guessing is not affected by difficulty. There's just some average gamma, log mean reaction time, and there's a different standard deviation sigma 2 than in the task engaged case. So there are two different standard deviations, and you might see where is my figure here? Well, we don't know. We can't tell from this plot, where your task engaged or not. So that's one of the problems we're going to figure out. We're going to figure out what the probability is, a posterior distribution on the probability of getting data from here, and the posterior distribution on the probability of getting data from the fast guess case, right? So this is a parameter. These are two parameters here. There are 1, 2, 3 parameters here, so 5, and then there's the probability parameter, the probability of getting data from one or the other, right? So 6 parameters. So right, so this is the way to describe the process in terms of the latent variable, this indicator variable 1 and 0, right? In the Bayesian implementation, we're gonna, of course, marginalize out the zeta, sorry, not the zeta, the z, this z or z, we're going to marginalize out. So we're going to use the other notation, right, which I showed you earlier. So we have these parameters 1, 2, 3, 4, 5, and then there's the probability parameter 6, that's p task here. And so we define some priors. Notice that the priors for gamma and for alpha, right? These are the average reading times in the task engaged case and in the task and the guessing case, right? They have the same priors, but they're just using some reasonably mildly informative priors here to set up the problem. And then we have the same priors for sigma and sigma 2, reasonably like mildly informative. So all this is familiar to you from the previous chapter. So we are not overly putting our weight on the scale, to give overly informative priors. And on the log scale, this is also pretty wide prior, but informative. It's not allowing completely insane values, going from minus infinity to plus infinity or something insane like that. So anyway, and then for the task probability parameter, we're just assuming a flat uniform distribution. This could be more informative actually, because a flat uniform distribution doesn't really actually make a whole lot of sense, because participants tend to be engaged when they're doing the task, they're trying to do their best. So one would want a more informative one, but we'll look at that later. Anyway, so now we will first generate some synthetic data to make sure that the model works as expected, okay? So we set up some simulations here. So what we're going to do is 1000 data points will be generated. The predictor is plus minus 0.5 coded, okay? And then you have the alpha, beta, sigma, sigma 2, gamma, and p task parameters with point values defined for them just arbitrarily. Notice that gamma has 5.2 and alpha has 5.8. That kind of represents the, assumption that when you're guessing, you tend to be faster, So anyway, so now if you, so if you compare the alpha and gamma, you'll see that the guessing mode has a much faster average reading time, right? Reflecting, that picture that I showed you earlier. Where is it? Where is it? Did I lose it? Here, right? That in oh no, sorry, this is actually wrong what I'm saying, because we don't really know whether the incorrect responses are always coming from the guessing mode or not. Although maybe in this model we are going to assume that. But in any case, so sorry, I just got sidetracked here. But what I want to say is that in the guessing mode, they will we are assuming in the simulated data that they will tend to be faster, and in the engaged mode, on average, they will tend to be slower. Okay? That's the assumption, which seems reasonable actually. Anyway, so um, for generating the mixture of response times, we're going to use the indicator variable z. So first we generate 1000, a sequence of 1000 ones and zeros randomly, right? Just a random Bernoulli process. And now we're going to use those ones and zeros to produce the 1000 response time. So if z happens to be 1, and this is the tidyverse syntax, by the way. This is not the built-in R syntax for if else, okay? So here, if z equals 1, that means task engaged, then you sample from the this log normal distribution. If, and that's the else case, right? This is the else case. If z is 0, this is implicit that z is 0 here, okay? So this syntax you may not have seen before. Then we are sampling from the guessing mode distribution, okay? So now once we've generated the reading times, reaction times, we can save it all in a simulated data frame. So we've got trial ID, we've got the X column, which contains the difficulty level, and then we have the simulated reaction times. You can look at the simulated reaction times, and they do look like the data that we had earlier. It's not very different, right? So if you go back from here to about 1000 milliseconds, so what did I have here, right? So it's about quite similar, okay? Maybe this has a longer tail, okay? Doesn't matter. So it's good enough, you know, it's producing realistic data. So now we're going to implement the mixture model in Stan, and the discrete parameter, as I said, you know, this indicator variable will be marginalized out. So we will write the model like this, right? As I showed earlier, it's a sum of two weighted log normal likelihoods. And so remember, of course, that the in Stan, we are going to work with the log space. So we're going to take the log of this entire term. Therefore, we put a log around the entire right-hand side. Okay. So what's about to happen next? I want you to remember that we are always, whenever we work with a probability density function, we are working on the log scale. So log normal LPDF is on the log scale. Okay, don't forget that now. That's a crucial point. So the syntax might look like this. So you might want to write a naive version, you know, of the model. So in the model we would write here that we're going to take the log of the sum of two terms. Okay, so here the log of the sum of two terms, these two terms. So we're literally writing out this statement now in Stan. Okay, so what we are doing is we write the probability here multiplied by the exponent of the log normal of the log PDF. The exponent is there because we were working in log space, and what we want in this equation is not the log normal in the log space. So we take the exponent of that. Okay, that's why the exponent is there. This gets very confusing because you see all these exponents and logs, and they're all like coming one after another. So you keep track of where you are. Okay, so this is in log space. Therefore, we are taking the exponent because we want to write out. We want to write out this thing here, which is not in log space, right? So anyway, so that's the first summoned, right? How do you say this? Like summoned? I don't know. And then the next part is 1 minus probability of the task engagement multiplied with again the other distribution, the fastest distribution. So we just rewrote this thing, this equation 11 here. Okay. So there are some problems, numerical problems in doing these calculations the way this is written here. So they can be overflow and underflow. So to get around that, what Stan does is it provides a function to write this kind of statement such that you don't suffer from overflow or underflow problems. You can find the details in the manual, or the user's guide or whatever for Stan. So you can see what that's all about. So the function that we're going to use is called log sum x, and I'm going to explain that now. It takes two elements and takes the sum of those two, right? So the other function we're going to use is log 1m x, and that what that does is it takes the log of 1 minus x. That's what that 1m is. Okay, these two functions is what I'm going to talk about next. Okay, but this one's easy. I don't need to talk about that. But this one requires some thought. Okay, so let's look at this. Okay, so the function log sum x defines a mixture on the log scale. Mixture on the log scale. The sum is that sum of two distributions weighted by their probabilities. Okay. So just in the abstract, suppose we have two summons. I should find out how to pronounce this. If you have two summons like A and B, and A is in log probability space, okay? A is log probability, and B is the log of the PDF that we are working with. In our case, that's the log normal, right? So A is the log normal of the PDF, log of the probability, and B is the log of the PDF we are working with, right? So if we say log sum x AB, what we are actually going to do is we're going to first, because A is in log space, we take the inverse of that function, which is the exponent, we get it back in the original space, probability space. So B is in the log PDF space with an exponentiation. We bring it back into there's a bracket missing. I'll put this back in later. So there should be another bracket here. I'm going to put, so we're going to get B back into the original space, right? So XA plus XB is going to take the two terms which are on the log scale and put them back into the linear scale and sums them up as A and B. Okay? And then these summed up terms on the linear scale are then converted back to the log scale by this log sum x. So this is what that log is doing. It's converting it back into log space. So that's why it's called log sum x. First, we're going to exponentiate the A and B's. Then we're going to sum them up. And we convert them back to the log space. That's the meaning of this function. Okay, the name, why it's named like this. I hope that's clear. I mean, it's really confusing. I always forget where the exponentiations and the logs are and why. So you have to unpack it slowly, and I hope this is clear now. So that's how we end up with the following Stan code. Okay, so the Stan code looks like this. Log sum x is going to be taking this first term, this is the first term, this is the A term, and this is the B term. Okay, A term and B term. So it's as I said earlier, the A term is in log space, so we have log probability of task plus the log of the log normal density, right? So that's the A term, and whatever is inside this density is all of this, right? So you don't have to think about that. The second term is also on the log space, like the second term B, which corresponds to B, is the contains everything on the log space, right? So log 1 minus p task and the log of the log normal density with the fast guess part of the model here, okay? So that's how this thing comes about, this log sum x thing, okay? All right, so again, I wrote down for your convenience what the two summands are, but what you need to notice is that this log 1 minus p task can be written, can be made more numerically stable by using this built-in function log 1 minus, log 1m, and all you put in is the p task. What this actually means is we're going to write log 1 minus p task, okay? So that's just a shortcut function that is numerically more stable. So that's how we end up with this one minimal change in the specification. So the model looks like this. This is the mixture RT stand model. Again, data block, number of rows in the data frame, which is 1000 in our simulated data. The predictor variable is a vector, and the response times or reaction times are also vector length. And notice that we are not modeling the subjects at all. Look, they are not anywhere. There's no hierarchical structure, nothing in this model, okay? It's just a simple linear model here. That can be added, of course, right? So you got the alpha, which is the intercept in the engaged mode, beta, the effect or difficulty in the engaged mode, sigma, the standard deviation in the engaged mode, and then in the guessing part, you have gamma as the average response time with sigma 2 as the standard deviation for that, and the probability of the task is the sixth parameter, which is bounded between 0 and 1. And notice that sigmas are also bounded from below by 0. Okay, remember that we don't have negative sigmas. Okay, so the model is pretty straightforward now because all the hard parts have been explained, So we have priors, a prior on alpha, prior on beta, just like before, prior on sigma. Remember, you have to truncate it, so we take the log of the complement of the CDF to truncate the normal distribution prior on sigma. And we do the same thing for sigma 2, right? Normal log the complement of the CDF as discussed earlier. And then we have the gamma prior, which is also straightforward. And then we have the beta prior on the probability of task engagement. Okay. So now for every data point in the data frame, we are going to now produce. So here it is. Look, every data point in the data frame is going to be coming from a distribution which is a mixture distribution. So here's the log sum x. This I've already explained, so I don't need to go through this again. And so that's the model, okay? So we fit the model, and unfortunately for us, we get a whole bunch of warnings. And the model is pretty horrible in the sense that what you'll see is that the R hats are all over the place, and number of effective samples is ridiculously low. So this model is not, you cannot ignore all this, okay? You have to deal with it. And so the trace plots, if you look at the trace plots, what you see is that the models are not, the chains are not mixing. You don't have fat hairy caterpillars. It's a total mess. And so the reason for that is that it's explained here. The two mixture components, the engaged mode and the guessing mode, they are exchangeable. That means in some cases, z equal to 1 means that you're in task engaged mode. Sometimes z equal to 1 means that you're in guessing mode. Okay, so the meaning of z1 and z0 is exchangeable here. Okay, and so it says that here, right? That um, right. So we are not able to identify which distribution we're getting data from, right? So we're gonna have to constrain the model a little bit, in order to make the model converge and not get run into this kind of trouble. And one of the things, in the model that we ignored is the assumption. So this is an assumption of the model itself that we are basing the code on, right? The assumption is that when you're in fast guessing mode, you're gonna be responding faster. Okay, so gamma is going to be a smaller value than alpha. Okay, that's one thing, right? So what we can do is that we can constrain gamma to be below some value alpha. So that means if you have a prior, let's say a normal 6-1 prior, normal 6-1 prior on gamma, we're gonna truncate it from above. Unlike the sigmas where we truncate at 0 from below, we're going to truncate the prior on gamma from above. Okay. All right. So this would actually make the model converge, but there's actually another constraint that we can put in, which makes theoretical sense. So as I mentioned earlier, a beta 1-1 prior, a uniform prior is pretty nonsensical because we know from doing decades of experimentation that participants are very cooperative generally, and they try to do the task honestly. They work on getting the answers right. They attempt everything, and so it would be more reasonable to have a prior on the probability of task engagement to be shifted closer to 1. So here we have one possibility. So this is constraining the model in some ways, right? In some specific ways, which make theoretical sense. So this is not an arbitrary decision that we are making. It's based on our reasonable beliefs about how people are involved in doing the task. So the model looks like this now. It's available in the bcox package, right? So all this doesn't change. This changes, right? The only thing that changes in the parameters is the constraint on gamma. So we say that alpha is an upper bound on gamma. So we're truncating gamma's prior from above, okay? And so everything else is the same here. Now we get to the model. In the model, alpha and beta are fine, sigma is fine, just like before, and gamma is different. Gamma, the prior on gamma is now being constrained, is being truncated from above. So what we are doing is we're subtracting not the log of the complement of the CDF, because that's what you do when you truncate from below. We are truncating the normal prior on gamma from above. Therefore, we take the log of the complement, log of the cumulative distribution function, not the complement of the cumulative distribution function. Okay, so so that's the only difference here. Okay, so notice here that alpha, what is alpha? Alpha is the parameter that represents the grand mean of the engaged task, right? That's what that alpha is here. So what we are assuming is that the gamma parameter is smaller than the alpha parameter in the engaged mode. That's what it means here. Okay. All right. So now we get to the likelihood specification, which is a mixture process here, right? Nothing changes here for us. It's just the same as always. Yeah, this statement is just the same as always. And so once we've controlled the upper bound of gamma in the parameters block here, right now, and once we've changed the prior, on the probability of task engagement. Here it is, right? Here it is. Now we don't have a uniform prior anymore. Okay. So what you make those two changes, and then we fit the model, right? And now we are happy because our hats are 1. Effective samples are no longer 1, 2, or 3 like before. So everything looks good. Okay. And if you look at the trace plots, you will see that everything's fine. So is this here? Yeah, you can see the trace plots here. Okay. So that's a simple mixture process with no hierarchical structure, but it illustrates the key, things that we want to take away from this lecture, this part of the lecture, the log sum x function and the log 1m function, right, that we had here, this one. Where is it? Yeah, log 1m function, right? These are two important pieces of syntax that or two important functions that were introduced here, and now you understand how a finite mixture process with two components can be modeled. In the next part of this lecture, I'm going to talk about multivariate implementation of the fast guess model. In this part of the lecture, I'm going to walk you through the multivariate implementation that's discussed in the textbook. Before I start, I just want to clarify something about terminology, because this is a very frequent confusion that I see. So there are two terms in statistics that are often confused. So one is multiple regression, and the other one is multivariate whatever, right? Models or whatever, right? So multiple regression really refers to there being one dependent variable that is modeled as a function of multiple predictors, right? That's what that multiple refers to. You cannot, so it would be technically wrong to say that this is a that this is a multivariate regression. Why is it wrong? It's wrong because there's only one dependent variable. Okay, this is a multiple regression because there are multiple predictors. So sometimes people use multivariate in place of multiple in multiple regression. So just be careful about that. In multivariate models, you will have more than one dependent variable, and that's the situation we're going to talk about now. Okay. So coming back to the notes, we until now in the simple model that was developed in the first part of this lecture, we were ignoring the accuracy information, right? So now we can implement a version where we model both the reaction time as well as the accuracy in the data. So this is just from the previous model, so we can ignore it. So The model that we are going to build now is that we are going to, of course, have the indicator variable, the Bernoulli, that's coming from a Bernoulli with some probability of getting a success, just like before. And we're going to have the same model as before for the reaction times, nothing different here. What's new is that we will have another part to the model where we are modeling accuracy, so correct or incorrect response in each of the n data points as either coming from a Bernoulli where the probability of a correct response is a new parameter called p correct, and that we sample from that distribution only when the indicator variable is 1. So this Bernoulli will decide in every one of those n trials whether we have a 1 or 0, and if there's a 1, then we are sampling the answers from this distribution. And one assumption in the model that we are developing is that the incorrect responses are being produced at chance. Okay, so they're just guessing basically, right? And so you're getting an incorrect response because of 50% probability of producing a correct response. So, so when z is 0, we are going to be sampling from a distribution with the Bernoulli probability set at 0.5, so like a point value, okay? So what we have that's new in this model is a new dependent variable. So there are two dependent variables, hence multivariate, and there will be one more parameter in the model, okay? That represents the probability of a correct response. So what we're going to have to do, of course, is to come up with a prior for the probability of a correct response. And because the researcher believes that the correct response is generally going to have very high, there'll be a very high probability of producing a correct response, right? So accordingly, if that's the case, then we will set up a beta prior where most of the probability mass is not exactly at 1, but it's pushed towards the right towards 1. Okay. So let's just simulate some response times like we did earlier. 1000 data points, and difficulty is coded as plus 0.5 minus 0.5. Here are the same point values as before for the parameters we already know about. The for let's see, yeah, so this is nothing new, right? This is all just like before. And and what's new in the simulation will be that we're also going to produce some accuracies based on the indicator variable, right? That will determine which Bernoulli we are sampling from. And here also what we are doing is this time we are using the R function if else. I don't know why there's an inconsistency in the code that sometimes we say if underscore else and sometimes if else. So that could be an oversight, but doesn't matter. What we are doing is if z is equal to 1, that's what this function is doing, then we are sampling from this distribution with p correct set to, where is p correct? Sorry, p correct is going to have, it's here, sorry, here it is, right? So we're just setting up a high accuracy of producing a correct response if z is 1. Otherwise, we're sampling from a Bernoulli distribution where there's a guess involved. 0 or 1 accuracy is produced if, remember what z represents. If z is 1, it represents that the participant is engaged in the task. If z is 0, then they're not engaged. And when they're not engaged, they're producing data from Bernoulli with chance level performance. Okay? So that's the accuracy data that we produce simulated This is the simulated reaction time data. You can make a data frame now that contains the trial ID going from 1 to n, the difficulty level, reading time or reaction time, and accuracy, right? So one can also create a column which takes the plus 0.5 minus 0.5 coded column X and renames it into something that you can use for plotting later on. Call it hard and easy. Hard is coded as zero point 0.5, easy is coded as minus 0.5. Hence, this function is doing um, creating a new column called diff. So difficulty, right? So now we can plot the simulated data to see if we get, roughly the right ballpark patterns. And so what we see is that for the easy versus the hard cases, one thing that we should notice is that the responses to the easy cases where the response is uh, incorrect, so the accuracy is 0, then the response times are faster, right? Because the accuracy will be 0. Um, yeah, so on average, you will get faster response times because um, whenever you produce a 0 response, right? So we will almost never get a 0 response from this distribution because the probability of getting a correct response is practically 1, okay? But we will get 0 responses from the guessing distribution. And the guessing distribution corresponds to the case where z is 0, and that is the situation where we are sampling from this this distribution where gamma is actually less than alpha, so it'll be faster. So that's what's reflected in this plot here, that the 0 responses will tend to be faster in both the easy and hard conditions. Okay, all right, so now we are going to write out the model in the usual way by marginalizing out the z values, right? So this is what we saw earlier. And because the response times and the accuracies are just assumed to be independent, we are able to multiply all these out. Okay, so this multiplication is possible between the log normal and the Bernoulli likelihoods because the accuracies and reaction times are independent. Okay, so this is what the marginalized version of the mixture model will look like. In log space, we would have to convert all the products to sums, right? So you have log, so here are the sums, right, that you see. And so this is all that I discussed earlier. And so the way the model will, and so the only thing that's changing now is this one term that's been added here to represent the likelihood of the binomial in the two situations, okay? So when you're task engaged versus not task engaged, right? So the stand model looks like this. This part, the data part, only has one new array. That's the accuracies, 0 and 1 values, 0 or 1 values that are integers, and there are n of those, so 1000. Okay? And then you have the parameters. These are all familiar, nothing new here. The only new thing is the probability of a correct response, right? That comes in the Bernoulli distribution where you're task engaged, okay? So there are only two new things here in the data block. One thing is new here and the other thing that's new is here, okay? But there's a probability, so it's constrained between 0 and 1. So the model looks like this. Again, I don't need to discuss the priors on the standard parameters that we've already seen. uh, for the probability of correct, we have a beta prior that pretty much pushes all the most of the probability mass towards 1. So that's what these two um, hyperparameters mean. And we keep the same prior as before for the probability of task. So now again, the main part of the model. So this statement, this here, right, will have to be written out in that syntax that I introduced earlier, log sum x. And here, the only new thing that you're seeing is this part here. For the first term, for the first summand, and for the second one, we see this one here, right? That's it. And everything else is just like before. So nothing much has changed there, okay? So set up the data with those four pieces of information, fit the model, and what we find is that we can fit the model to both response times and accuracy, okay? And the parameter estimates seem pretty okay if you look at them. And wait, did we constrain gamma here or not? Where was it constrained? Gamma was constrained here. That is, upper bound is alpha, so gamma is less than alpha. And in order to express the fact that we're truncating the gamma, just remember that this term has to be added, to be included, right? So you subtract out the log of the CDF, right, to truncate from above. Okay, so then once all this is set up, there's a for loop here that generates row by row. It generates data for every set of samples from the of the parameters. Okay, so now oh sorry, I just went back to the STEM model, but now we see that the output's okay, our hats are fine, everything looks good. And there are more checks to be done than these. Like right now we're just doing a quick informal check to see if the parameters look okay, but later on we'll do more checks once we start building a hierarchical version of this model, okay, which will take subject level variability into account. So then the next part of this model development, you can see that we are incrementally building up the complexity of the model. So the next part of the extension to the model is to take the instructions into account. So the instructions were as follows. Subjects were either asked to focus on accuracy or asked to focus on speed. So as you can imagine, if the subject is cooperative, which they almost always are, if you tell them to focus on accuracy, they will try to be as accurate as possible. That will slow them down, right? If you ask them to focus on speed, then they will go as fast as possible. Reaction times will be faster, but the accuracies will be lower, right? So, and in fact, when we do these kinds of speed accuracy experiments, we sometimes give an incentive to the participant, actual money, for finishing the experiment fast, or for finishing the experiment with a higher accuracy, as high accuracy as possible, or an accuracy above a very high threshold, right? That way you can induce the participant even more dramatically to do the mode of the task that you want them to do, right? But here that's not the case, I think. So what we're going to do is we're going to add a predictor, and the speed incentive, the predictor will be called x2 here, and the speed incentive will be coded minus 0.5, and the accuracy incentive with plus 0.5. So we're going to fit this kind of model on what? We're going to fit it on the log odd scale because what we actually assuming what we want to model is that the instructions focus on accuracy or speed are going to affect the probability of task engagement, right? So the probability of task here, right? So what we will do is we will use the equivalent, of the p logit function. So we fit the model in in log odd space, which goes from minus infinity to plus infinity. Having fit the model in log odd space, we use the the mathematical uh, analog of the p logit function in R, if you remember, and get back the probability of task. Okay, so this is the common way that we will be writing the stand models, right? Because in stand there is a function called inverse logit, right? So one can just write the log odds model inside the inverse logic function in stand, and then model the probabilities that way. All right, so what's going to happen now is that where is it? Sorry, is it further down? Yeah, this is coming up later. Sorry. So the model that we are now going to fit is going to have x2, which is the task, the instruction modulation, right, affecting the probability of task. So here's the probability of task as before, that produces the indicator variable that tells you whether there's the participant is engaged in the task or not. This is 1, participant is engaged. If it's 0, that means that the participant is not engaged. And that's coming from a Bernoulli response time. The response time distribution is just like before, right? So this was the easy hard manipulation, right? Just like before, nothing new. This is all the same as before. And here also everything is the same, right? So what will change now is that we won't just have a prior on task, we will now need priors for no, we won't have a prior on task, but we'll have priors on alpha and beta. These are two new parameters now that will determine the probability of task, okay, depending on the instructions, okay. So that's the change now that will happen. So one can come up with some priors for the beta parameter. So the beta parameter is here, right? This is the effect of the instructions, right? Now, the way we've set it up is that we have a fairly broad prior, because this is in log odd space, right? Beta task is in log odd space, so there's a fairly wide prior on this. But one could have set up a directional prior also, because if your theory strongly suggests that what was the coding? If if you're, let me just go back and look at this, right? So if you have an accuracy incentive, then what should happen is that your probability of task should go up. So if this is plus 0.5, this should be positive, because that will lead to a higher probability of task engagement, okay? So that's the prior on beta. So now we also have to set up a prior on alpha now. And you could have set up a directional prior, okay? Normally we don't do that. Normally we don't set up a directional prior, because we want to allow the possibility of the theory being wrong, right? So it could be that if you ask people, I mean, it's ridiculous, but if you ask people to focus on accuracy and the probability of task engagement goes down for some weird reason, you want to theoretically allow that. So once we have the data, of course, if the data are consistent with the theoretical predictions, which I would imagine is the case, then this is just this is an uninformative prior essentially, right? So we are not imposing too many constraints on the beta parameter here. So the next problem is to choose a prior for alpha task, right? Remember what alpha task was? Alpha task is this term here that represents the average in log space, the average task engagement, regardless of the instructions, right? Because the instructions are coded plus 0.5 minus 0.5. Think about the contrast coding chapter and the sum coding stuff that we discussed earlier, okay? So now we have to come up with a prior for alpha. And so what one can do is one can set up actually, so I may have lied earlier when I said that there is no prior anymore on beta, on probability of task, because what one can do is one sets up a prior on the probability of task and back transforms it using the QLogit function in R, which in mathematics would be logit, right? So you define a prior on the probability of task engagement as a beta 82, and then pass it through the logit function, which in R would be the QLogit function, to get in log odd space a prior for alpha task. Okay, so having defined all these priors, we now are in a position to check if the priors make any sense, right? So we can do that by generating some data. So here, look, what's happening is first you define a prior. We are simulating data here. Sorry, this is not defining a prior. You're simulating data from a beta distribution A2, the two parameters, the A and B parameters, right, which are called shape 1 and shape 2 in R, and we are producing 1000 sequence of 1000 probability values here, okay? And then beta task is coming from a standard normal, just like I defined here. Beta normal is coming, we are simulating data here, okay? So we are just going to generate some 1000 data points that represent the beta task, the prior coming from the standard normal, the prior being the standard normal for beta task, right? And then what we are doing is we are producing a vector of 1000 probabilities, 1000 because we're going to produce 1000 data points simulated for the easy and the hard task, and that is done here by taking the log odds equivalent of the probability of B task here, see that? Taking the log odds equivalent by passing it through the QLogis function and then multiplying. So now we are in log odd space here, okay? And so we are now adding the beta term here. So there'll be 1000 values of beta here multiplied with 0.5. And then we pass the whole thing through the QLogis function, PLogis function, that gives us back the corresponding probabilities for each of the 1000 rows in the data frame. Okay, we do this for the easy case, for the easy conditions, and for the hard condition, right? Same setup, except that we have minus 0.5 because of the contrast coding for hard and easy. Okay, so this is how one ends up producing 1000 probabilities corresponding to every row in the data frame that we're going to generate. So then you create a table, a data frame that contains the difference between the easy and hard task probabilities. The purpose of this will become clear in a moment, because what we can then do is simulate some data from those priors, based on those priors, and then look to see what the priors imply for the difference between easy and hard conditions in the experiment. Okay, so that's what you're going to look at now. Let's look at the histogram, and this shows us that the priors that we have set up are reasonably okay because they are non-committal. They lead to a non-committal probability. This is the difference of probabilities. So this is not difficulty. This is just the difference of probabilities. Okay, for the easy and hard, between the easy and hard conditions. So we see that it's somewhere between minus 0.4 and plus 0.4, and it's symmetrical, right? So it's a reasonably uninformative prior on that represents that the difference in probabilities between easy and hard. Okay, so that was just a sanity check to see what the purpose of this simulation here was, to check, because it's not obvious when you look at the prior specifications, it's not obvious what that would mean in terms of the difference between easy and hard task probability of engagement. So that's why this simulation was done, just to see if these priors are reasonable. They are not totally insane. Okay, so that's what you see here, that it's not too crazy. All right. Actually, you can go and play a little bit, with these priors, and then look at this plot, how this changes as a function of the prior specification. You get a better feel for how the priors translate to a difference between the two probabilities. All right, so now we're going to generate a new data. So now that we are convinced that the priors, the relevant priors that we just looked at, are not insane, we're going to generate some data. Again, we're going to generate 1000 data points, and here's the predictor X, which represents the easy versus hard difficulty, and the two predictors that we now have. We also have another predictor, which is the instructions that are given to the participant. Okay, so just to make us do a sanity check, you see that we have total of 1000 data points and 250 in each of these cells. So it's a fully cross setup here, right? Easy, so easy, hard, and speed and accuracy, right? We have the instruction. So we have equal numbers of data points here that we will generate, okay? Once we've set up the predictors here, right? And the predictors are coming up here. We created these here. We created a vector of 1000 numbers here, okay, of plus 0.5s and minus 0.5s. Then come the point value specifications for simulating the data. So these are all the numbers that I've already discussed. This is the probability of a correct response when you're engaged. This is the probability of the average this is slightly confusing, because probability of B task, which is set at 0.85, is representing what? It's representing this, right? So the average probability of task engagement in log odd space is what this is alpha, is this alpha here, and the corresponding probability is p task here. Okay, so where was I? Here, look here. So remember this is what I'm trying to get at. So we had defined a prior on the probability of B task. The probability of B task here is actually representing the log odds equivalent of the alpha task. parameter. Okay, that turns up here. So I know this is a bit, there's lots of moving parts now in the model. It's going to get even worse, okay, when we include hierarchical structure, but the model is attempting to take into account all aspects of the design now. And so this involves a certain amount of complexity. So just work systematically and slowly and internalize every addition to the the model design. I know that it's complicated, but eventually you'll be able to internalize it. Okay. So that's that. We are setting up the probability of B task here at 0.85. Okay. And then the beta task is set at 0.5, and so now we're going to generate the data. The QLogis function is going to take that probability of B task, which we specified as 0.85, and going to convert it to alpha task, right? Because that's what it was. And it's going to turn up now in the log odds equation that we showed earlier, which is here, right? So here's log odds space. We are now producing a probability of task engagement as a function of the instruction, right? So these are the alpha and beta parameters right here in log odds space. And that's why we pass it through the plogis function to get back the value in the probability space. This is a vector of 1000 values, plus 0.5, minus 0.5, and we are getting a point value here and a point value here. This point value, which was defined in log odd space, oh my god, this is so confusing, right? So beta task is in log odd space, alpha task is computed is via the probability of B task, okay, by passing it through the log odds, by passing it through the logit function. I've been saying plogit and qlogit when talking about the R equivalent, but actually it's plogis and qlogis. I guess they did that to make everybody's life harder, right? So they probably, the statisticians, they don't like to make things easy. So if it's like an inverse logit, they're calling it logis. I have no idea why. Maybe logistic, it's short for logistic or something, right? But nevertheless, it's confusing, so don't get confused. This is just the DPQR family of functions for the logistic, transform. Anyway, so coming back from my digression and my rant, is the indicator variable is now generated as a result of this using this p task, probability value that we just generated here, and now we produce 1000, a sequence of 1000 ones and zeros randomly, and then use those just like before to produce the reaction times, and use those just like before discussed earlier to produce the accuracies. Okay, and then everything is put together, trial ID 1 to 1000, the predictor easy hard plus 0.5 minus 0.5 coded, reading times or reaction times generated randomly here, right, as a function of the randomly generated indicator variable z, and then the accuracy, same story, and then you have the instructions added. So these are the 5 pieces of information that go into the data frame that is containing the simulated data now. Okay. So now we can, once we generated the data, we can now go ahead and look at the the simulated data by facet, right? By easy, hard, in engaged versus easy and hard in speed versus accuracy instruction settings. Okay, so the plot should look something like this. Where's the plot? Here it is, right? So, okay, so let's look at this. These are the easy conditions, the two easy conditions, which are either accuracy focused, that's the instruction, accuracy or speed, and the hard conditions where the instructions are to focus on accuracy or speed. Okay. So again, this is the simulated data now. Okay. So what you're seeing is again faster response times when the response is inaccurate. I explained why that is the case. In this, it's based on the way we set up the parameters and the model, and so it looks reasonable here. Okay, the simulated data doesn't look totally insane in my view. So so we're going to make heavy use of this log inverse logit. Inverse logit is the p-logis function in R, right? That's the equivalent in stan, and we'll be applying that. So we had seen it earlier, and we will also use something called log 1 minus inverse logit. This is for the case where you want to model a probability. So here we are modeling with where is it? With on the log scale, the inverse logit is representing some probability that we are modeling here, probability x, and the probability 1 minus x would be modeled then um, with the log 1 minus inverse logit function. Okay, that's coming up in the stand model, but just to mention that it's going to come soon here. Okay. And in the stand model, the logit function is the equivalent of the q-logis, function in R. So you can see that this probability of task engagement, which represents the alpha task, okay, has to be converted to logit space, to log odd space. So that's what this function is doing. And then this is already in log odd space, right? The priors defined on beta task, and that prior is assumed to be in log odd space. So in the stand code, we'll be using this function here, and these other functions will also turn up now for back transforming to probability space. Okay, so you should just become familiar with the issue that there will be, so I guess I should say this one more time. Okay, so you need to be very clear about how, whether you're working in log odd space or probability space, right? So these are two options, two things. The q-logis function in R, and the what is it called? The logit function, I think, right? Yeah, the logit function in stan are the equivalents there. Okay, and if you want to go into probability space in R, you would use p-logis, right? And in stan, you would use inverse logit, right? Like I said, we never want to make life easy for anyone. Okay, we always want to define everything differently. That's what people are like. They'll all come up with different conventions just to make your life miserable. Okay, so anyway, you just have to keep this in mind. I'm sorry about that. Okay, and of course, because we're working in log space, there will be a log before the inverse logit, etc., etc. Right? All right. So So let's get going. So we're going to be using also the log sum x function, as you will see in a moment. And so let's get moving on this. Right, so the stand code looks like this. You'll see that the stand code is actually not so painful once you keep in mind all these back transforms between log odd space and probability space. Okay, so what we're going to do is in the data block, we're going to define the number of data points, the vector containing the predictor easy hard coded plus 0.5 minus 0.5. Remember, vectors have to be real numbers. Okay, and then we have another vector for the response times. Also, all of these are 1000 length, and accuracies are going to be integers, right? So you don't want to use a vector for that. And anyway, there will be no algebraic, matrix algebra operations defined on this. So we will use array, okay, for accuracy. And then for x2, which is the speed or accuracy instruction, that's also vector x2. And then there's this same thing that you saw a long time ago, this only prior indicator variable, which will be either 0 or 1, and we will use that to generate either prior predictive or posterior predictive data. So if you've forgotten that, go back and look at the, I think it was the Stan Programming Language Introduction lecture or chapter to see how that works out. Okay, so you can just search for only prior in the textbook, the online textbook, and you'll see how we use it if you've forgotten. Okay, anyway, but you'll see the code in a moment. So this is the information that goes into the data block. So this will be part of this 0 or 1 value. It will be just one number, okay, 0 or 1. That will go into the list containing the data that is fed into the stand code, okay. Then the parameters are all familiar to us. 1, 2, 3, 4, 5, 6. These parameters we've seen before. And notice that we have a parameter for beta task, but we don't have a parameter for alpha task here, because that will appear in the that will be created as a function of probability of B task. Okay, and this is the probability of producing a correct response. So that's how the parameters are set up. And now we get to the model. This line is clear. This is the prior on alpha. Alpha is the reaction time, okay? So the reaction time alpha. This is the reaction time beta, dependent on easy or hard, responses. And then you have the sigma parameter, which is truncated as usual. Gamma parameter is constrained from the right by alpha, so it has to be less than alpha, right? So that's why you got this line here, and this is the standard, this is a 6-1 normal prior in log space. And then you've got sigma 2. Sigma 2 was the standard deviation in the guessing case, guessing response reaction times, right? So we have a prior for that. And then we have the beta task prior, which is in log odd space, standard normal, if you remember. And then the probability of a correct response in the engaged condition is very high, right? The prior assumes that the probability mass a priori is shifted to the right towards 1. And then the probability of average task engagement, right? So the alpha task parameter, right, that we will derive from this, that's assumed to come from a beta 8-2 distribution, right? So the assumption is that on average people are pretty engaged with the task, okay? So now we produce the data generative process for the end data points. We're going to define the model for every row in the data frame. And so I showed this earlier. We are now creating this line here is creating alpha task, and this is the beta task as a function of instruction, right? And because we are passing it through the logit function, everything is in log odds space here, and we are saving that as the log odds task as a function of these two parameters, right? And instructions. So then we get to the famous, log sum x function, and this function has um, um, right. So this function, the first term here is taking the log inverse logit. That's what I was just talking about a few seconds ago. This inverse logic function on the log space, right? It's taking this thing. So what was this? This was actually the probability of task engagement, right? So that's what we're converting back to a log probability space. Right? And then we have the log of the log normal PDF, right? That models the reaction times plus, right? This was just like before. We are now adding a Bernoulli term here that's modeling the accuracy. So here we are modeling two dependent variables. That's what makes the model multivariate now. We're modeling two different dependent variables here, and the accuracy is a function of the probability of correct responses. Okay. So that's the first term, right? In the log sum exp function. Remember, the second term is now talking about the situation where you're not engaged, right? So that's the log 1 minus inverse logit, right? Because the probability would be 1 minus whatever the probability of task engagement would be. So that comes here, and then the art. So this is the non-task engaged situation, the mixture process, and here we are generating data with the gamma intercept only and the sigma 2 standard deviation, right? And then the new term that's added here is the Bernoulli, which assumes a guessing process, right? So there's a point value here. There's no parameter here. There's just a point value given for the theta parameter in the Bernoulli, and that's producing the chance level response in the non-engaged setting. Okay. So that's the basic setup for the model. So this whole thing represents the model starting with this from this for loop and ending in this for loop here. So if only prior is equal to 0, so if only prior is not equal to 1, that means if it's equal to 0, then this will be true, right? And that's when this code will be triggered, right? So and so if only prior is set to 1, then this will be 0. So we will not do any generate any posteriors for the parameters, right? So the generated quantity to quantities block will now remain invariant because the generated quantities block will produce predicted data or predicted accuracies, right? Based on the parameter specifications and the model specification that we have that I described earlier, and that's in this code here, right? And the parameters will either be the posteriors, all the parameters here, 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 and all the other ones will be either posteriors that would have been computed if this condition were true, right? If only prior was set to 0. And if only prior is set to 1, then when this code runs, it will produce prior predictive data. So you can check now whether um, the prior predictive distributions will come out the way that you would expect, right? So this is the actual data, okay? But this will not be used when doing prior predictive checks. If you set only prior to 1, then that data is only there as a placeholder. It's not going to be involved in producing the prior predictive data. So if you look at the prior predictive distributions running the stand model, and if you look at the output here, you see that reaction time prior predictive distributions are not crazy, right? Pretty okay. And the differences in RTs between the easy and hard conditions is not is reasonable actually, right? So that's what we get from the prior predictive check. You can run this model yourself to see how this goes. And right, so I just explained that. And then you can take the simulated data. Well, I said it was the real data, but I meant the simulated data, and then fit the model to that by setting only prior to 0. Okay, so now the generated quantities block would produce posterior predictive data, right? So we fit the model, we see the parameter estimates here, everything looks reasonable, and it seems that the model is able to generally recover the parameters. So the next thing I'll talk about is the hierarchical implementation of this model, right? So adding hierarchical structure to it. The last topic that I will cover in this lecture relates to the hierarchical version of the fast-guess model. But before I get into that, it may be useful to quickly review how where we are at and what the previous model was that I discussed, because there are many moving parts. It's important to get everything straight in your mind to see how the model comes together, right? So I just made a little note here that explains in full how the non-hierarchical mixture model is set up, how it's defined. And this is the model that takes instructions into account, but it's not hierarchical. Okay? And I will also relate the model specification to the STAN implementation code so that you can see the connection between the model specifications and the code in the model. I won't talk about the more obvious things in the STAN code, like prior specification is now trivial. It's the actual implementation of the log likelihood in the mixture process that requires some careful thought. Okay, so the very first thing to notice in the model that takes instructions into account. Instructions is the variable x sub 2 plus 0.5 minus 0.5 coded for accuracy and speed respectively, right? So what we're going to do is that the instructions are going to modulate how much task engagement will be involved, in the participant's mind. So we are going to make the probability of task engagement a function of an grand average task engagement on the log scale, and the probability of task engagement will be modulated by this variable x2, which is the type of instruction being given, focus on speed or focus on accuracy. So this slope parameter here, which is also in log odds space, will determine what the log odds would be of the probability of task engagement. Okay. Now, because we are fitting the model in log odds space, recall the logistic regression stuff, we will back transform that to probability space to get the probability of task engagement for every row in the data frame. Okay. So this will be so what you're going to get is some grand average probability of task engagement. That's this term here. So remember, this is the logic term. So we're giving as input to the logic a probability of task engagement, an average probability of task engagement, and converting it to log odds with the logic function. Okay. And this is the second part, this part of the equation. This is in log odds space. This is defined. Beta task is defined in log odds space. And this is um, the type of instruction being given. Okay. So what you end up with, because there are n data points in the data frame, you're going to end up with a vector of values depending on what the value of x2 is. Okay, so that will determine what the log odds are, and that will then determine the log odds of task engagement. So that will be created in the stand code. So this is going to come up again in a moment. And then the priors that have to be defined are on this guy, alpha task and beta task. But instead of defining a prior directly on alpha task, what we are doing is we're defining a prior on the probability of average engagement. So that's the beta 82 prior, and then converting it back to log odds, right? So the priors on the probability of B task, and then gives us back the alpha task value based on this prior. Okay, and then for beta we have a standard normal prior, right? So these two priors, the priors for the alpha and for the beta, are taken into account. Then the next part of the model defines the probability of task engagement, right? So this is what we've just figured out here, right? As a function of x2, and there will be a vector of x2 values, right? So there will be different probability of task engagements in every row of the data frame, okay? Depending on what the value of x2 is, right? So where am I? Sorry. Yeah. So this probability of task engagement will determine the value of the indicator variable, 1 or 0. When it's 1, that means the participant is engaged. If it's 0, it means the participant is not engaged. Okay. So this is randomly generated in the simulated data, but it's defined in the model to be generated from a Bernoulli, where the probability of 1 is this quantity here. Okay, so then we come to the reaction or response times. Though that's a mixture process depending on whether z is 1 or 0, right? Of course, this will be translated into a statement that marginalizes out the z. So the z's never appear in the stand model because stand can't deal with discrete parameters. But it's convenient to see the model like this. So this is the task engaged generative process. This is the non engaged generative process. That's the mixture. And then the parameters, so the 1, 2, 3, 4, 5 parameters, they have the priors that are specified here. And then we come to the second part of the multivariate model, where we are also modeling the accuracies, so the zeros and ones in the data frame, which tell you whether the response was accurate or not. So the accuracy when the participant is engaged will come from a Bernoulli with parameter probability of correct, for which I'll just give you a prior. And when the participant is not engaged, the assumption is that the participant is guessing, right? So the accuracy is coming from Bernoulli process, but the probability is 0.5, okay, of a correct response. So now coming back to this new parameter here, the probability of correct was coming from a beta prior. So we are assuming here that there's very high probability of producing a correct response if you're engaged, which seems reasonable. So that's the model, okay, in mathematical form. In Stan, the mixture of likelihoods in log space that we will define looks like this. So first think about the model not in log space. So we're talking about the generative process that is produced as a result of the mixture. So this is now we are marginalizing out the z, right? This is that formula that is in the lecture notes. So we have the probability of task engagement. We have so this is the part where the participant is engaged. Okay, so in this case we multiply 3 terms because we are assuming that accuracy is independent of reaction time, etc. So we multiply these 3 terms out to get the first term, and then for the non-task engaged part we have these 3 terms that we multiply. Okay, so that's, if we convert all this to log space, so then you get the log likelihood right. So this is supposed to represent a likelihood function where you're given reading time, reaction times, and accuracies, and you're estimating all the parameters in the model, right? So it's a function of the thetas. That's why it's a likelihood. So now it's a log likelihood of theta, and there we are taking this. We are now going to be converting all the products into sums. These 3 products become sums here, and this stuff I had explained earlier. So yes, so this, you will see the Stan code in a moment, and so all this this whole thing is now wrapped around in a log. Okay, that's why this log is now encompassing this entire thing here. Okay, so now we have sums of terms here. So first what we are doing is we are converting everything to logs. These 3 products are being converted to logs so that we can talk about sums instead of products. Then we exponentiate it back because then we're going to take the log again, right? Because the log exponent is the inverse function for the log. So these logs serve to allow us to sum up the 3 products, and then we exponentiate back to get back on the original scale, and then we take the log. Okay, so it's a bit hairy to think about here, but it's straightforward. Okay, so the point is that we want to get to the log likelihood in the end, and so the code, the log space version of the likelihood, is what Stan implements, and that's what that function log sum x does, right? If you recall the discussion earlier, it's taking these logged up, all these are logged up values. This is the first term, right? And this is the second term. They're all in log space. Then we exponentiate internally, right? Because this is the log sum exponent, it's exponentiated, and then a log is taken, and then everything's summed up. So that's how the model is set up. So one thing to remember is this might be confusing, that you've got a log of p task here, right? We are going to rewrite, this is the model, what I'm showing you here is the model where you don't take the instruction into account. That was the first model we discussed. So that's why we could just write log p task, because the probability of task engagement was just a standalone thing with no, you know, effect of instructions here. This we are going to change, and this is also what we're going to change now, because we want to get the probability of task engagement and 1 minus the probability of task engagement on the log scale. We want to get it as a function of the instruction that was given. So the change that will happen in the model is that instead of writing log p task, we are going to write log inverse log odds task, right? So this log odds task, if you remember, I discussed it at the beginning of this section, where we produce on the log odds scale, we produce the effect, the probability of task engagement on the log odds scale as a function of the instruction, right? So we create this term here first, and then we plug that in here. Okay, so this log odds term is fed in here into the inverse logit function and converted to logs here with the inverse log inverse logit function in stan. Okay, so that's one change. This replaces the simpler statement we had earlier. Right, so what's happening is that because this is a for loop, okay, going from 1 to the number of data points that we have, when n is 1, then it will look up the first row in the data frame. It will produce one numerical value, log odds task, just one value. That's why this is a real and not a vector, right? But earlier I had said, you know, that, where did I say this? Earlier I had said that this is a vector. In the for loop, this is a real number that will be produced, because this will be produced n times. So if you think of all those n log odds task values, that's what I meant when I said that it's a vector. Okay, eventually it could be seen as a vector, but in the code, because we're using a for loop, we're going row by row. What's going to happen is that we are where am I? Yeah. So what's going to happen is that we are going to produce one real number each time in each of the n rows, and that represents the log odds of task engagement at that particular row in the data frame. Okay, so that number goes in here in each of the n iterations, and then you get back the log probability, right, of task engagement as a function of whatever the task, the instruction is at that particular row in the nth row of the data frame. That's one thing that changes. And the other thing that changes is that instead of writing log 1 minus probability of task, if you look at the old model, when we didn't take task engagement into account, we had this. So this will also change now, right? This will become log 1m inverse logit, and it will also take 1 minus the log odds, 1 minus, well, the probability of task engagement, because the inverse logit will convert it to probability, and then 1 minus the probability is what is being computed here, right? And then eventually it also converts it to log. log scale. Okay, so that's the only thing that changes. So that's what I'm explaining here. So basically that's the model. Okay, so you need to be clear about what's going on. And so now we are going to switch to a hierarchical version of this model, which is also straightforward because you know chapter 5, you know how to make a model hierarchical. But mathematically what's going to happen is in the reaction times, this is the only place where we will add hierarchical structure. Okay, so what you're going to see here is that if you remember in the reaction times mixture process, whenever the participant is task engaged, then they have an average uh, um, average response time on the log scale, and the effect of the easy or hard trial type, so the easy or the hard level of the conditions it determines what the reaction time would be in the nth row, right? In the nth row, this x will either be plus 0.5 or minus 0.5, plus 0.5 for hard, minus 0.5 for easy, right? So this number was originally being multiplied with beta to produce the reaction times or response times in the engaged condition. Similarly, same thing here. So what's new now is that the intercept will have a bias subject adjustment, varying intercepts by subject, just like in chapter 5, and we will have varying slopes adjustment. So different participants are assumed to have different average response times and different effects of the easy and hard manipulation. Okay, that's what gives it the hierarchical structure. Now, because we have the U matrix, you know, if you have 20 subjects, you have a 20 by 2 U matrix, right? So we're going to assume a, oh wait, sorry, I made a mistake here. So the gamma is also assumed in the non-task engaged case. The gamma is also assumed to have by subject intercept adjustment. So there's actually 3 dimensions to this U matrix. So if there are 20 subjects, this U matrix will contain 20 rows and 3 columns. The first column will represent the by subject adjustment to the grand mean intercept in the engaged task. The second column will represent the by slope adjustment to the beta parameter in the task engaged case, and the third column will represent the intercept adjustment in the non-task engaged case. Okay, so that's why this is going to be 3-dimensional. So the variance covariance matrix will have 3 dimensions. So this is not a bivariate normal, it's a, I don't know what you can call it, a trivariate normal. Okay, 3 dimensions. So we're going to have 3 standard deviations now for U1, U2, and U3, right here. U1, U2, and U3. So 3 standard deviations. Each of them has some reasonable truncated prior. And for the correlation matrix that will go into the variance covariance matrix, we have an LKJ prior with parameter 2. The standard regularizing prior, you know, that downweights +1 and -1. So you can simulate some data with 20 subjects that we can use for, you know, evaluating the model. So each subject will deliver 100 trials. So that means there are 4 conditions, right? So there's easy and hard and speed and accuracy. So it's a 2 by 2 design basically, right? So we have 25 trials for each level in the data frame. Okay, so we have 20 subjects, 100 trials, alpha, beta, sigma, sigma 2, gamma, and beta task, and the probability of beta task, alpha task converted from probability of beta b task, sorry, not beta task, probability of task engagement is 0.85, probability of task engagement is back transformed to log odd space to get the alpha task, right? So we go from here to here, from just like I just explained at the beginning of this section. then the probability of a correct response is just basically set to a very high in the engaged mode, right? And then we have the three taus. It's a vector now, 0.2, 0.005, and 0.3. So this is the intercept adjustment standard deviation. This is the slope adjustment, which is typically very small. So that's why it's set to a small value. And this is the intercept adjustment for the gamma, which again would be pretty large, right? So correlations are all set to 3.3. So that's how the data is now built. We have the number of data points we'll have is the number of subjects times the number of trials. So 20 times 100. And so then what we do is, this is just bookkeeping now, okay? So here we're creating the X column, the X2 column, then the subject IDs, right? And each of the subjects will be repeated 100 times because there are going to be 100 data points for each subject, and then the trial trial ID is provided. Okay, so trial ID is just increasing like one by one, stepwise. So these are this column is just marking the row ID of the data frame. It's not part of the data frame as such. It's just showing you which row you're looking at, and it's not in the data frame, of course, right? So there's X2 subject and trial, and you can build the correlation matrix now for the adjustments in the matrix U. So we first create a correlation matrix with 0.3 in all the off diagonals, right? And there will be a 1 everywhere along the diagonals. So you build up the correlation matrix by just plugging in ones into the diagonals and 0.3 in the off diagonal. So that's what you get in the end. Then from the correlation matrix, we can build up from the correlation matrix and the standard deviations. These, right? From this vector of standard deviations, we can build up the variance covariance matrix. We need that to generate the U's, the adjustment. So here, the variance covariance matrix is built up now by taking the diagonal matrix of the tau U vector, multiplied with the correlation matrix, and then post multiplied with the diagonal tau U vector, just like we discussed in chapter 1 and in the, I think in the STAN programming language chapter as well. So now we just use the mass libraries or mass packages function MVR norm, multivariate norm, and this creates the 20 by 3 matrix that contains all the U's, the adjustments for the subjects. You can also check now whether the correlations between the three are roughly 0.3, because we have very little data here, so they're not exactly 0.3, but they're close enough, in the ballpark. So this is the correlation between the 3 columns in the U matrix. Okay, it's just a sanity check. You can also check the standard deviations of each of the columns, and those are also roughly the numbers that we have put in. So now we create the simulated data, right? So stimuli is this matrix that we create. So we're going to use this matrix to generate the simulated data now, because there's no data right now here. It's just setting up the skeleton. This is the model matrix for the reaction times, and for the accuracies. Okay, the multivariate situation. So we generate the data now, and we take the stimuli skeleton that we just looked at, and we run the Bernoulli function to produce the probability of a correct task, right? So we have fixed values for these, and so we have point values that we defined earlier, if you remember. I went through it rather rather quickly. So here's the beta task from the log odds that we defined, and the alpha task log odds that we defined in terms of the probability of task engagement, which we had specified here. Okay, so we are just generating a vector called prob, which we're generating a vector called z that contains ones and zeros, right, as a function of instruction. Okay, so and then the reaction times or response times are produced in terms of whether the z value is 1 or 0, just like in the mathematical model. And so we are just implementing the mathematical specification I showed you earlier, right? This part is being implemented here, okay? And then the accuracies are being produced again in terms of whether z is 1 or 0, right? And that's where's the accuracy part? Probably comes later. Here, right? That implements this part, okay? So when you're not engaged, it's 0.5, and here 0.5. Otherwise, it's the probability of correct, which is set to a very high value of 0.999 or something like that. So anyway, that's the accuracy column created, and then the difficulty column is created as hard and easy, and then the emphasis instruction column is created as accuracy or speed. Okay. So if you were to look at the data, simulated data now, this is the simulated data, it would contain not just that skeleton of stimuli, it'll have new columns here for the easy, hard, difficulty thing, and for the emphasis, and then the reaction time for each row, and accuracy for each row, zeros and ones accuracy. That's what the simulated data will look like. Okay, and then now you can look at graphically, you can see if the data look reasonable. They look pretty similar to what we had seen at the start of the lecture. So what we are seeing is that in the easy conditions, what you see is when the accuracy is, when they're incorrect in their response, is generally faster. We saw this pattern earlier, right? And speed and accuracy, if I'm not seeing much difference here, but maybe it's this is slightly faster. You can see that in the easy conditions, right? There are some slow values here which are not much more compressed over here, but I can't really visually tell the difference between these two here. This should have been a little bit more compressed. Maybe one needs to adjust the parameters for simulating the data, but anyway, it's just roughly in the ballpark, you know, it's okay. So now, because it's just simulated data, eventually we fit the real data. So this model is implemented in the mixture underscore H model, and we are going to use the Cholesky factorization just like before, right? So everything you learned in the chapter on Stan implementations of hierarchical models now is going to be deployed. Okay, so just go back and revise that if you've forgotten all that. So now the model specification, the information that goes into the data block is the number of trials, the x vector, the x2 vector, which are the predictors, right? Plus 0.5, minus 0.5, the dependent variables, right? That are coming in. Notice that the reaction times are real numbers, so they are vector. Arrays are used for accuracies because there are 0, 1 integers, right? So you don't need real numbers there. And then you've got the number of subjects that will be needed for the hierarchical structure, right? Because you need to look up in the U matrix now, you need to look up which subject you're talking about, you know, because that will determine the adjustment term for that subject. And then the subject IDs, right, goes from 1 to number of subjects, and it's also an array because these will be integers and not real numbers. And anyway, we are not doing any algebraic operations on these or on these, right? We're not going to be doing any matrix algebra on that. eventually, I mean, if you implement it as a matrix setup. Anyway, so now we come to the parameters alpha, beta, sigma, gamma, sigma 2, probability of correct, probability of B task, and beta task, right? All these are familiar to us now. Then there are the three taus, the three between subject variability. So it's a vector with three elements, okay? The lower bound is 0 because it's a standard deviation. There are three standard deviations. Then you have the now here we are doing the the familiar thing that we did earlier, where we first get in order to produce the U matrix, we're gonna first get the Z's from a standard normal, and then we're going to do the Cholesky factorization, blah blah blah, and get back the U's, okay, just like we did earlier. So then the last thing comes the Cholesky factor. It's a 3 by 3 matrix, the correlation matrix. So the Cholesky factorization will also be a 3 by 3 L sub U matrix. And so then what we are doing next is that we're going to generate the U's by, so this will be a matrix, right, with 20 by 3 matrix, right, and it will be generated by taking the ZU's, which are coming from a standard normal, and then doing a diagonal pre-multiplication, right, of the tau U's and the LU's to get back the U's, right. So this is all discussed in the Stan programming language section, right, where we discuss how the hierarchical model is implemented with the Cholesky factorization. So if you've forgotten that, just go back and look at those lecture notes. So now we have the U's. That's the big achievement here. We have the U's. And so now the model specification starts. We begin with the easy stuff, which is the prior specification. So I don't think I need to discuss any of this. All of this is clear, and P correct, everything is all discussed. We've discussed all of the stuff up to here. Here's the LKJ2 prior on the Cholesky factorization. That's a built-in function, right? It's a built-in function in Stan. And then, of course, for the ZUs, we are going to have a standard normal, which is also a built-in function. This is all on the log scale, right? This is all log. Okay, so then the model specification begins. Same thing again. We have the log odds task like before, and then log sum x comes again, and the same thing all over again. The only thing that changes now in the code is that we are putting in not just the alpha plus beta, but the adjustments by subject. It's that easy. Now we're just taking the U matrix, looking up the subject ID in the nth row of the data frame, extracting the first column from the U matrix to get the nth subjects, intercept adjustment, etc., etc. This is for the slope adjustment, and this is for the non-engaged, for the non-engaged case here, right? You see the intercept adjustment. That's it. There's nothing else that changes. I mean, it's just like little, Lego blocks that you need to put in for adding hierarchical structure. Once you get used to the Cholesky factorization, it's pretty straightforward. Then you can extract in the generated quantities, you can pull out the row U's, the three posteriors for the row U's by just taking the Cholesky factor, which is actually a parameter in the model because it is a prior specified for it. You can use it to convert to the correlation matrix, and then look up the correlation matrix, the posteriors of the three correlations there, okay, that are informed by the data. So you set up the data as a list form, and then extract the model from the bcogsci package, right, and then fit the model, and then print the posterior summary. And you'll see that the model estimates are pretty straightforward. The three correlations you can 1, 2, 1, 3, 2, 3. Yeah, these are the three correlations you can see. along with the 95% credible intervals, right? And so these are the, and the fit seems okay, right? If you look here, everything looks fine. And so we can fit the hierarchical extension. It's not a big deal, right? Now you can do a basic sanity check because we are working with simulated data. So we know what the true values of each parameter is. Therefore, you can check whether the model is recovering the posteriors represent the true parameters or not, or are able to capture or recover or contain the posteriors, whether they can contain the true parameters or not. So here's the figure coming up here, right? So in this figure, what you that was just code that is all just MC recover hist is the function. So you can look at this code later. It's just standard stuff. So what we produce here is the posterior distributions are in blue here of each of the parameters, and the true values are the vertical black lines. So everything looks pretty much okay except for maybe a few things here. The probability of this is the alpha, you know, the alpha task parameter, the average engagement, right, which was set probability of average engagement was 0.85 if you remember. So this one is somewhat higher here, okay? So it's kind of overestimating task engagement, or maybe that is what the reality is. And the probability of a correct response is somewhat lower as well. But it doesn't look, overall it doesn't look terrible, okay? So it looks fine. Right, so now that it's more or less okay, the model seems to generally recover most of the parameters. We can now try to fit the model to real data. So we set up the contrast coding just like before, and the main problem that we will now face is the data are not sparse and the model is complex, so it could take a while before you can fit these models. So in order to just illustrate what's going to happen, we just take 600 observations from each subject, and that proceeds like this. You just take samples of 800 from each subject and then proceed work with that. So now this is the shortened data set with only 600 data points per subject, and then you set up the data list in list form and then fit it with the same model, right? And then you end up with all kinds of warnings. And if you look at the output, you'll see that the R hats are all over the place. It's a complete mess. So this is not good, right? If you look at the trace plots, I mean, over there, yeah, you can see that the chains are not mixing at all. It's a spectacular non-convergence, right? So what can be done? One thing you can do is to try to simplify the model, right? And one way to simplify the model is to hard code the assumption that the probability of a correct response is 1, right? So during task engagement, when people are task engaged, they will give a correct response with probability 1. This is a pretty strong assumption. This is a trial and error stage. Now you can try out different things to see if you can get the model to work. This can get a bit tedious, if you're working blind. And here, of course, the code is provided to you, but in real life, it could take some time to figure out what to do. Okay, but simplifying the model is always a good first step. Okay, to see what you get. Right, so this is an incremental process. of adjusting the model. So now this next model with this hard-coded value for probability of correct responses is here in the bcoxi package. And now if you refit the model, so the model looks like this. What's happening is that there's a new section, there's a new block here called transform data, which puts in the probability of a correct response in the task engaged case to be 1. Okay, that's the only new thing here. Everything else is pretty much the same. Yeah, it's all the same, and so I don't need to discuss any of this. This is where the 1 will turn up, you know, in the Bernoulli, in the task engaged case, right? When you're task engaged, accuracy will be 100%. All right, so everything's the same. We set up, we run the model, and this time everything converges, right? And some interesting things to look at are that the sigma for the task engaged case is much smaller, half the size of the sigma in the guessing case. Right? That's what we're getting from the data. And the trace plots look good, right? All good. And so basically what we can take away from this model, of course, given the assumptions we've set up, okay, so this doesn't necessarily represent the true generative process. It's based on our theoretical assumptions and some compromises that we had to make because of the extreme complexity of the model. So it seems that the instructions seem to have a strong impact on the processing mode of the subject. If you look at the beta task parameter, which tells you the effect of instructions, the value is pretty high and it's in the expected direction. So that means if you emphasize accuracy, you get a higher probability to be in task engaged mode. See that here? This number here and 95% credible interval, you're going from 65% to 92%, right? So it's a pretty tight interval here. Oh, sorry. Yeah, right, yeah. This is not a percentage. I'm sorry. This is in log odds. So log odds 0.79, and I got fooled by these percentages here. So log odds is 0.79 with a 95% credible interval going from 0.65 to 0.92. Okay. All right. So that's one thing that we learned, and the other thing was that the guessing mode seems to be much noisier because, as I said, sigma 2 is twice as large as sigma. Okay? 0.2 versus 0.4 or something, right? As I also already mentioned, like we could look at the posterior predictive data and see if our model is doing pretty okay, but that's not a guarantee that we have not overfitted the data, and it's also not a guarantee that the model is a good fit. In the end, we would always have to do some model comparison using, for example, k-fold cross-validation to decide whether one or the other model is a better representation of the underlying generative process. Right, so you could use Bayes factors or cross-validation or whatever. I have lots of papers on my homepage where you would be able to find, my examples of using Bayes factors and cross-validation, sometimes in the same paper, to decide between competing models. And the code is available if you want to look at it. So the posterior predictive checks can be done, of course, and So there's a function called GQS in Stan, which has the advantage of generating posterior predicted data of any size. So normally, when you produce posterior predicted data, it's going to produce data with the same size as the data that we put into the model. So we can get past that by using the GQS function. And the way that works is that you define your model, right? And in the in the usual way, you generate some posterior predicted data here, and then now we can generate responses from 500 simulated experiments in the following way. You take the code here is saved in bcog package as mixture h2gen, and then you save that model, okay, as a character string, and then produce the you take the fitted model and then you pass it through the Stan model function and save the result of that here in gen model, right? And then we are going to take the what are we going to take? Just a minute. See, the fitted model that we had fit earlier, that was the model that we had fit earlier, right? We are now going to take that model and that's this one here, and we are gonna generate 500 simulated data sets. See that? 500 simulated experiments, right? From that fitted model. And when we do that, as a matrix, we're going to save the draws of the parameters. So all the samples from the parameters in the fitted model are extracted, okay? And because we specified 500 separate experiments, we are going to what we're going to do is we're going to take those draws from the fitted model. Okay, maybe I should have run this and to show you how this works, but it would take too long. I don't want to do this right now. I'll do it in the class. Okay, so this will be easier to see once I do it step by step. Okay, so then once I've got the parameters from the fitted model, I'm going to put it in here into the GQS function under draws. The data has to be provided, right? And then this gen model is the model that which I just showed you here, is being taken out from the bcog package, right? That mixture h2gen Stan model, that's being provided to the GQS function. So the GQS function takes as input the model that will produce the posterior predictive data, takes the actual data as well, because then you can compare the actual data with the posterior predictive data, and then it takes as many draws as you want from the posteriors of the parameters, right? That's what we did here. There's some syntactic sugar here that you have to pay attention to. So it says here the argument of the matrix drop of the matrix, this argument drop needs to be set to false, otherwise R will simplify the matrix into a vector, right? So you don't want that to happen because there are going to be different parameters. Okay, so that's the input to this GQS function. Actually, I must say I've never used this function because generally speaking, posterior predictive checks that I use when I'm fitting a model are just a basic sanity check, and I'm happy producing as many data points as there are. But I'm just telling you this about this because it's in the chapter. I don't actually use it at all. So because I've never had a need to produce a certain number of experimental data sets, I would produce all 4,000 data sets, right? Anyway, so if there are 4,000 samples from each parameter, so you can look at the reaction times or response times in the posterior predictive model and compare it to the real data. So we are extracting now from the posterior predictive data. We are extracting here's the predicted data, and that will be compared with PPC, posterior predictive check, density overlay plots using the real data, which we had put in here, right? And so we can look at the output, and so you can see that the fit is reasonably okay compared to the actual data. That's the black line, and the blue lines are the posterior predictive data. One thing that's odd is that the difference in reaction times for the easy versus hard conditions was in the data was quite large, but in the model the estimates are pretty low. So this is a kind of misestimation here. So it's not doing that well. Maybe that's due to sparsity in the data. One could try that with the full data set. Just run the model overnight, 12 hours. You can see what happens with the full data set. Maybe things get better. You can also look at some specific details about the predictive distribution, the posterior predictive distribution. So here the next figure will show a simulated data set in black overlaid with the real observations, right? So again, we're using the extracting the predicted accuracies, and we're going to compare with the observed reaction times and accuracy. So what the black is the posterior predictive, and these light colors are the actually observed data, So you see that there is some underestimate. The data being produced in the posterior predictive data is a bit shorter than what's actually observed in the data set. So there are some shortcomings in this model. Right here also there's misestimation, but it's not the end of the world, I would say, right? So if you're going to use cross-validation to compare this model or with another competing model, right? And as I said, I have many examples of this in our published work. So if you go to my homepage, look at our publications, there's lots of papers where we use cross-validation for this. Then what you would have to do in the generated quantities block, you would have to extract the log likelihoods, because the log likelihoods will be used in the K4 cross-validation step, right? So all this is discussed in the K4 cross-validation chapter. One important thing to remember is that if you're comparing models, they have to have the same dependent variable or variables. If it's a multivariate model, variables, right? You can't be comparing different dependent variables in the competing models. That's something to watch out for, okay? So basically what we have achieved in this lecture is that we saw increasingly complex two-component finite mixture models, and we gradually built up the complexity. If you go to the table of contents, we gradually built up the complexity. First, a very simple model, Then, oh well, it was here, sorry. Very simple model of the fast gas, implementation of the fast gas model. Then a multivariate implementation taking reaction times and accuracy into account. And then a multivariate implementation that takes instructions into account. Oops, I didn't mean to do that. Let's go back. Right, that takes instructions into account. And then finally, we get to the hierarchical implementation of the fast gas model. The way to keep track of all this information, I think, is to focus your mind on this little note that I've prepared, because this summarizes the models, and all that changes in the hierarchical model, right, is in this part here. In this part here, right? Here, we just add some hierarchical structure by subject variability to the two intercepts and to the slope. That's it, right? So once you understand this base non-hierarchical model that takes instructions into account, the rest just is all the stuff that we already know, just applied in a new setting here, okay? So these mixture models are actually really useful, because you will often find yourself in a situation, well, not often, but you can find yourself in a situation where a mixture model is needed and is a much better explanation for how the data were generated. And this can have important theoretical consequences, right? So I will probably discuss a specific example that illustrates, how good how important this kind of mixture model is for evaluating whether one or some other theory makes more sense. I have several papers on this topic, but I'll give you a simplified version of that story. So that's it for chapter 17. I know it's a long and complicated chapter, but it's worth learning how mixture models work, because you will eventually need them if you're going to do any Bayesian modeling. So it's worth investing some time into understanding how they work. And once you get used to the basic, setup of the mixture process in the log, all the interesting action is happening in the log exp, log sum exp function, instead. Once you get that, then it's you can pretty much adapt it for your particular problem.